Matt Singer, yum!
Hello, and welcome to another Math Singer video. My name is Eric, and today we're going to be talking about addition. In particular, we're going to question why it is we are generally taught to add from right to left whenever it seems much more natural to add in the manner in which we read, which is from left to right. Let's get started. Let's begin with a relatively simple problem. 472 plus 316. Now, this particular problem poses no difficulties whatsoever adding from left to right. We can just go right down the columns. 4 and 3 is 7. 7 and 1 is 8. 2 and 6 is also 8. We wind up with a final answer of 788. Easy. But why does it work? Well, let's take this apart a little bit at a time and ask what we're really being asked to do in disguise. So 472 is really, what is that? 400 plus 70 plus 2 added to 300 plus 10 plus 6. In fact, whenever we read these numbers, 472, what we're really doing is verbally adding those three numbers together, the 400, the 70, and the 2. 472. The T on 70 is actually short for 10. So 4 hundreds, 7 tens, 2 ones. Added to 3 hundreds, 1 10, 6 ones, 316. And we can add these together in any order that we like because, well, addition is commutative, which means roughly that we can rearrange the numbers in any order that we like and add them in any convenient manner that we wish. So a convenient manner for this particular problem would be to add the 400 and the 300 together, giving us 700. Add the 70 and the 10 together to give us 80. And add the 2 and the 6 to give us 8, for a total of 788, which was the answer to our original problem. This next problem looks a little bit more challenging. We're going to add 867 to 379. Well, what happens whenever we do that? Well, if we proceed exactly as we did in the previous problem, we're going to get an expression that looks a little bit unfamiliar. Adding 8 and 3 together, that gives us 11. 6 and 7 is 13. And 7 and 9 is 16. And so, if we read our answer the way we read the answer to the previous problem, we have 11 hundreds 13t16 as our final answer, which actually there's nothing wrong with that. It's not the way society usually likes to hear the answer, but it is exactly right. The answer is going to be a total of 11 hundreds added to 13 tens, 130, and another 16. So if we break this up into its component parts as we did before, let's see, what is this? 800 plus 60 plus 7 added to 300 plus 70 plus 9. Well, what we're going to get is, well, there we go with our 1100. I guess we usually read that 1100, but 1100 is just fine. 60 plus 70, well, that's 130, which in fact is 13t, 13 tens, right? 13 times 10 is 130, plus another 16. So we get exactly what we said before. We get 11 13T 16 is the final answer. Of course, society usually likes us to re-express this in another way. Usually in the tens column, we don't want to have a final number that is larger than 99, 100 or up. And so what we're going to do, let's take that 100 and add it to the 1100 over here. So instead of 1100 in this column, we actually have 1200. 1100 and 100 is 1200. So we could re-express this, right? This is the same as 1200 plus 30. Remember, we took the 100 and we added it to the 1100 to give us 1200 over here, plus the 16. Of course, in the ones column, we don't ever want a digit that is larger than 9. At least society doesn't want a digit any larger than 9 in the ones column. And so we'll take the extra 10, right? There's 6 ones. We'll take that extra 10 and we'll add it to the tens over here. So instead of 30, we'll have 30 plus 10 is 40. So this is 1200 plus 40 plus 6 for a total of, let's see, what is that? 1, 2, 1246. That's the final answer. Now, could we have done that without going through this longhand? Yes, in fact, we can, and it's really quite easy. Let's look at this problem one more time. Instead of writing the answer the way we did initially, 1113 to 16, let's do this. Let's write the 1100 first. So that was the 800 and the 300 giving us 1100. So giving us this first part in our component evaluation of the problem. Then we'll add the 60 and the 70. Well, 60 and 70 is 130. And then we'll add the 7 and the 9, 16. And I think you'll see that if we add those three numbers together, what we're going to get is 1,246. 1,246 is exactly the answer we got before. But you know, we can actually do this in even more of a shortcut manner, because after all, the zeros in the 1100 don't actually have to be written down. Whenever we add those to the column-wise addition later, it's not going to add anything to the total. Same with the 130. There was no reason to write the 0. Right? We got the 1 in the hundreds column, the 3 in the tens column. We do have a 0 in the ones column, but we don't really need to write it. And so I'm going to do this problem one final time. And we're going to do, and this is how left to right multiplication can be accomplished. We'll take the 8 and the 3 and we'll add them together, minding the columns that we're putting the digits in, right? So 8 and 3 is 11. Now, really what we've done is we've added 800 and 300 and gotten 1100. The other two zeros are sitting there, but we don't really need to write them down. The 6 and 7 added together, well, that's really a 60 and a 70, giving us 130. Minding the columns, let's see, 130. So 1, 3, 130. Don't really need to write that 0 down. Just imagine it's there. Write it if you like. 7 and 9 is 16. Write the 1, write the 6. And then as a final answer, I have 1, 2, 4, 6 as my final answer. And of course, that is the answer we got before. Now, this seems to take up a little bit more space than we might need to take up. So I will do this one last time just to show you how I might go through exactly the same process, but in a shorter amount of space. Go ahead and add the 8 and the 3, giving us 11. Add the 6 and the 7, giving us 13, but let's write it this way, 13. And add the 7 and the 9 together, giving us 16, 1, 6. Total 1, 2, 4, 6. And that is left to right addition. As a quick demonstration of the versatility of this left to right algorithm, let's show you how we can add, let's say, 4 numbers together. Again, we're going to do it column-wise. 4 and 5, 9, plus 3 is 12. 12 and 6 is 18. Second column, 7 and 8 is 15, plus 1 is 16, plus 2 is also 18. And I'll write it that way to save space. 2 and 7 is 9, 9 and 8, 17, 17 and 2, 19. Write the 19 that way. Right, so we've got got our 18, another 18, and our 19, and whenever we add those together, 1999 as a final answer. For our last demonstration of the left to right algorithm for addition, we're going to add 2 numbers together that have infinite decimal expansions. Now I want to point out that in the traditional right to left algorithm, we can't even begin this problem. There is no beginning point on the right. But the left to right algorithm, we can move straight on. Add the 3 and the 8 together for an 11 decimal point. Add the 7 and the 9 for a 16, which I'm going to write this way. 8 and 7 is 15. 5 and 9 is 14. 7 and 7 is 14. 8 and 9 is 17. 5 and 7 is 12. 7 and 9 is 16. And then we would continue. I guess the next number here would be for continuing the pattern. That would be a 7. For continuing the pattern, let's see, 7, 8, 5, 7, 8, 5, 7. This would be an 8. I guess the next digit here would have been or the next number would have been 15. Whenever we add the 8 and the 7 together. Anyway, whenever we finish adding, we're going to get 12.76558337. Let's see, what's this next digit going to be? Well, let's see. I guess I'm going to have a 5 sitting here. I'm going to have a 9 sitting here. I guess the next digit would be, so this is 14. Next digit would be a 6. And I believe we're going to continue the pattern now, 765583. And I believe we're going to have 765583, 765583 forever hereafter. Anyway, the left to right algorithm is superior in this manner, at least. Let's go back now and look once at the right to left algorithm and see what advantages it might have, if any. Let's revisit one of our earlier problems, 867 plus 379. Reviewing what we did before, we found that we could add the 8 and the 3 to get 11, the 6 and the 7 to get a 13, 7 and the 9 to get a 16, and then whenever we add the final digits, we get 1, 2, 4, 6, right? That's what we did before. Now, if we were to use the right to left algorithm on this problem, 867 plus 379, what were we taught to do with grade school? Well, what we were taught is to start over here on the right, add the 7 and the 9 together first. 7 and 9 is 16. 16 doesn't fit in the ones column. And so what we did was we separated the digits. We took the 6, and we put it down there. And when we took that extra 1, and we threw it up here. Now, that is equivalent, is it not, to the 16 that we got before, but it was so unnatural for us to separate those digits. And think about it, if you're first learning addition, that really is a very unnatural process. You're adding 7 and 9 together, getting 16 and putting the digits of 16 in completely separate places. And then adding this column. So this column now has a 1 and a 6 is 7. 7 and 7 is 14. Well, 14 doesn't fit in the tens column, so we'll put the 4 there. We'll carry the 1 up there. We have our 14, right? There was the 4 from the 14. And, but the digits are separated. We have the 1 sitting up here in the hundreds column. And we'll do our final addition here. 1 and 8 is 9. 9 and 3 is 12. And of course, we're going to get the same answer as we got before. A little smudge there. But the process was so unnatural. There is an advantage, but I believe it's a very minor one. This takes a little bit less room. We also had to do a separate addition in our initial pass through the problem, but frankly, I think that our method, our left to right method, is far superior as far as understanding what it is we're doing. Each step of the process is a natural one, and especially whenever children are learning addition for the first time, this seems to be the superior method. Once you understand what you're doing, maybe you do want to resort to the method that takes less space, which incidentally was done because, well, this algorithm was formulated whenever school children were using slates, and there wasn't a whole lot of room on that slate to do the arithmetic process of addition. And so this was considered the superior method. It saved on space, but it was short on understanding. We hope you've enjoyed this video. It's been the first one that we've made since the inception of our website, www.mathsinger.com. From there, you can navigate all of the Mathsinger videos and go to various links, YouTube, Facebook, and can even leave us a review. We hope that you will visit www.mathsinger.com, and we look forward to seeing you in the next video. Take care.